So the attenuation of the light intensity as it travels into the material will be quite strong and depends on the conductivity. So if this is our distance into the metal, where y equals 0 is the surface of the metal, and we have some initial intensity I naught, then from what we've seen above, what we'll get is a negative exponential, a decaying exponential, as the light travels into the metal. If we take the point a I naught over E, the 1 over E point, then we can define that as a particularly a characteristic depth referred to as the skin depth or the penetration depth. And so the penetration depth or the skin depth is just 1 over alpha. And 1 over alpha, when y equals 1 over alpha, we have e to the minus 1 in our expression. So as a couple of examples for copper in the ultraviolet wavelength, so if it's about 100 nanometers, then the penetration depth is about 0.6 of a nanometer, and for the infrared then it's about maybe 6 nanometers. Now, just to kind of give you some reference to that, that is 0.6 nanometers is an incredibly small distance. I mean, the light will only see the first few layers of the lattice structure. It won't go into the material any depth at all, really. We've seen that delta is inversely proportional to the penetration depth, and so it's also inversely proportional to the conductivity. Good conductors have small skin depth, and that kind of fits with what we see in the real world. If we pick up a metal, then generally we can't see through it. It's opaque, and that's because the light gets absorbed very quickly at the surface. We can make very, very thin films of metal, and they can then become partially transparent. So if you think about the photographs of the astronauts on the lunar surface, the photographs usually show them with a gold visor. And that's because the visor was coated with a very thin layer of gold. It's a very effective way of having strong attenuation of the light, but with very, very little weight. As I said, relatively few electrons in the metal actually see the transmitted wave. And even though each of those electrons will absorb very, very strongly, actually not that much energy is dissipated by them. Most of the light that hits the surface is actually reflected rather than absorbed or transmitted. And this continuum model, this idea of the metal, the slab of metal being like a box of gas molecules bouncing around, with the electrons bouncing around like that, that works reasonably long at long wavelengths in the infrared, but not so much at the shorter wavelength, where the theory becomes a bit more complicated.